So a quick recap before we start. In the last couple of classes, we defined various terms like the metric, norm, and inner product over spaces. We also defined limits of sequences, what are open sets, closed sets, and compact sets over a particular metric space. We saw examples of each of these, and we also studied limits and continuity of functions and the derivative and gradient. We also saw that if the derivative, if all the partial derivatives with respect to each of the components is continuous and differentiable, then the derivative is essentially the Jacobian, correct? But that's not always the case. In particular, the Jacobian makes sense for functions over Rn, and in this class we'll also see an example where we have a function defined not over Rn, and you can't directly use, let's say, the Jacobian to find the gradient or the derivative. All right, so before we continue, any questions? Okay, so let's do a couple of examples for derivative of multivariate functions. So again, this is sort of an example that we saw in the last class, but let's do it once again. Suppose I have a function from Rn to R, f of x equal to the 2 norm of x the whole square. Okay, what would be the derivative of f of x? That would be 2x transpose. I can write this as x transpose x. You can do it any way you want. In the previous class, we studied the derivative of x transpose ax for any matrix A, of which this is a special case. But even otherwise, this is also equal to the Jacobian. So it is equal to dou f by dou x1, dou f by dou x2, and so on, dou f by dou xn, and that just turns out to be 2 times x1, 2x2, 2xn, which is just 2 times x transpose. Okay. So this is a simple example. Now let's look at a more complicated example. Suppose I have a function defined on matrices instead of functions defined on Rn, correct? Now, if you recall the definition of the derivative of any function, of any multivariate function, we said that some linear operator D is the derivative of f of x if the following happens. You take f of, say, f of some vector z minus f of x minus d f of x z minus x. So if this quantity if this has a limit as z tends to x and this is equal to 0, then we say that d is the derivative, right? Now let's parse this. So this is true for vector valued functions, right? So if f is a function from, let's say, Rn to Rm, then this particular definition makes sense. But in general, what is it equal to? So in general, this would be the derivative. For this to be the derivative, I just have to replace this quantity with an inner product between the derivative and z minus x, right? So if I have f of z minus f of x minus the inner product between f of x z minus x. So this would be some norm divided by z minus x. If this limit equals 0, then this is the derivative. Okay, where here I'm assuming that f is some function on a metric space to R, okay, where I can define an inner product. So for example, if z and x are matrices and f is a function over matrices, then effectively what this boils down to is the function of the matrix of matrix z minus the function evaluated on matrix x minus the inner product between these two matrices. So this quantity should tend to 0. Okay, so let's see a concrete example of this particular case. Okay, so for this I need to define an inner product on matrices. We've seen inner products on vectors, so we need an inner product on matrices. I claim that the following is an inner product for matrices. So if I have two matrices A and B, then the trace of A transpose B is an inner product. Okay, so we have to first verify that this is indeed an inner product. Does it satisfy all the properties required? What is the first property that we need? It should be symmetric. It need not be greater than or equal to 0 for all A and B. So firstly, it should be symmetric. Is it symmetric? Is f of A comma B equal to f of B comma A? So the trace of A transpose B, is this the same as the trace of B transpose A? It is. So it is symmetric. Secondly, if I take the inner product of a matrix with itself, then this should be greater than or equal to 0 and should be strictly greater than 0 as long as A is non-zero. Okay, so trace of A transpose A, this is greater than or equal to 0, and if A is non-zero, then this is strictly greater than 0. Okay, in fact, there's an even easier way of checking that this is an inner product. So what would be the entries of so this is what the trace of A transpose B is simply the sum of the diagonal elements of the matrix A transpose B. So if I take A transpose B, what does it give me? Let's say that A is a matrix with column vectors a1, a2 up to say an transpose, and matrix B has columns b1, b2 up to bn. So this would give me some matrix. I don't care what the off diagonal entries are. All I care about is the diagonal entries because I just want the trace. So what would be the first diagonal entry of this matrix? It is simply A1 transpose B1. What would be the 2, 2 element? It is A2 transpose B2. Similarly, for the nth element, this is just AN transpose BN, right? So what is the trace equal to? So trace of A transpose B is equal to, sure, so it is summation I equal to 1 to n AI transpose BI. But what is this equal to if I expand out AI transpose BI? Yeah, correct, it's the dot product between A and B, but I want it in terms of the entries Aij and Bij. Correct, so this would just be summation I equal to 1 to n, summation j equal to 1 to say m. In fact, the matrices don't even have to be square. As long as A and B have the same dimension, this is well defined. This would just be Aij, Bij. So it's just like taking the element wise product of all of the two matrices and then summing all the entries up. Correct? Does this look familiar? Okay, but even more, it's just if I sort of vectorize the matrix, right, then that just corresponds to the standard inner product of the vector form of those two matrices. Correct? So essentially I take the matrix, I stack all the columns to form one really long vector. The inner product between those two vectors is just equal to trace of A transpose B. Okay. So that's in fact an easier way of seeing that this is actually a valid inner product. All right, but the way of writing this as the trace is sometimes helpful because you can utilize the property of trace, and we'll do that in a little bit. So we now see that the trace of A transpose B is a valid inner product. Okay. Now let us try to find the derivative of a somewhat complicated function. It's a function that we've already seen. Suppose I define f from the set of all positive definite n by n matrices to R. So f of A is equal to the log of the determinant of A. Right. So the underlying space is the space of all n by n symmetric positive definite matrices, and the function is the log determinant of A. My goal is to find the derivative of this function. Okay. Now in this case I can't simply use the Jacobian, right, because this is not a function on all n by n matrices. So let's see how we could try to find the derivative. So we will have to resort to the first principles, right, the definition of the derivative of a matrix. So how would we do it? Effectively what we need is this particular definition. So suppose I take matrix Z to be equal to matrix X plus some other matrix delta X. And I'll want to let delta X to sort of tend to the zero matrix. Again, this is defined over the set of all positive definite matrices. So both Z and X should be positive definite. Okay. Where Z and X are positive definite. Now, what properties do we know about positive definite matrices? Yeah. Correct. So Y transpose Z Y should be strictly greater than 0 for all non-zero vectors Y, and Y transpose X Y should be greater than 0 for all non-zero vectors Y. What else do we know about Z and X? Okay, it's symmetric. What can I say about the eigenvalues of Z? The real and positive. So all the eigenvalues okay. We'll revisit this in the next couple of classes, properties of positive semi-definite and positive definite matrices. But for now, let's use these as facts if you have not seen this before. The third property that we have, if you've not seen it before, is that if Z is a positive definite matrix, then it has a square root, a positive definite square root. What do I mean by that? So there exists some matrix. So if Z is a positive definite matrix, then there exists some other matrix which I'll call Z power half. So this is a matrix. Okay, so Z power half is another matrix which satisfies Z power half times Z power half equal to Z. All right. So there is a positive definite square root of a positive definite matrix. That's a property that we will use. Okay, and also since they're all positive definite, all the eigenvalues are real and positive, each of these also have inverses. So Z has an inverse, Z power half also has an inverse. And I'll call Z power half the inverse of this square root to be Z power minus half. Okay, so these are properties that we know about Z and X. Now let's try to evaluate the derivative. What do we need? In case we are able to show that f of Z minus f of X, or so minus the inner product of some matrix D with Z minus X divided by norm of if this tends to 0 as Z tends to X, then we are good. Or another way of looking at it is, if I'm able to write f of Z as f of X plus inner product between D and Z minus X plus some function which vanishes faster than the norm of Z minus X, then I'm done. If I can find a matrix D such that I can write f of Z, any f of Z, as f of X plus inner product between D and Z minus X plus some quantity that decays faster than z minus x, I'm done. Okay. This is also equal to f of x plus inner product between d and delta x plus little o of the norm of delta x. Okay, are you with me so far? Okay, so let's write down f of z. F of z, which is f of x plus delta x, is the log determinant of x plus delta x. Now I'll use the first one of the properties of the positive definite matrices that we've seen, that x has a square root. I can write this as log determinant of x power half the square root of x times the square root of x plus delta x. Which is the log determinant of x power half times I plus x power minus half delta x x power minus half times x power half. Okay, I just took on the left hand side, I take x power half out. So I can write delta x as x power half times x power minus half times delta x, because it's just the inverse of x power half. Similarly, on the right hand side, I can take x power half outside. So this effectively, I've introduced an x power half, x power minus half, and on the right hand side again I've introduced another x power minus half times x power half. Yeah? Which one? Sorry, which one? The first term. So this is x power half into x power minus half, which this one? Correct. That came out on the right hand side. All right. So let's do it step by step. So I have this, right? I have log determinant. Make things convenient. Let's look at x plus delta x. I can write this as x power half times x power half, right, plus x power half times x power minus half delta x, x power half, sorry, x power minus half times x power half. Okay, now let me take an x power half outside. So this is x power half times x power half plus x power minus half delta x, x power minus half, x power half. Okay, now I can write this x power half as I times x power half. Let me take another x power half outside, but not on the left, but rather on the right. Okay, it's just a trick that I'm going to play. This is equal to x power half times I plus x to the minus half delta x to the minus half times x to the half. Okay. Now, why am I going through all of this? Ultimately, I want to write f of z as f of x plus something. Okay, so I need to get f of x, which is log determinant of x. I somehow have to get that term from this particular quantity. Now, just by looking at this, can I get log determinant of x? What is determinant of a times b? So it's determinant of a times determinant of b, correct? So what is determinant of this matrix times this matrix times this matrix? It is just the product of those determinants, right? So f of z equals the log of determinant x power half times the determinant of I plus x to the minus half delta x to the minus half times determinant of x to the half. Okay, but again, now these are real numbers, right? So I can essentially change the order as freely as I want. So what is the determinant of x to the half times determinant of x to the half? That is just equal to determinant of x. So this is equal to log of determinant of x times determinant of I plus x to the minus half delta x to the minus half. So this is just log of this quantity plus log of this quantity. But what is log of determinant of x? It is just f of x. So this is, I've been successful in writing this as f of x plus something. I plus x to the minus half delta x to the minus half. Okay. Now I somehow have to be able to write this as sort of the inner product between delta x and something plus some quantity that is vanishing, right? Plus some small error term. And this is where we need a few tricks. So I have determinant of this. Suppose that lambda 1, lambda 2 up to lambda n are the eigenvalues of x to the minus half delta x to the minus half. Okay. If this is the case, then as delta x tends to 0, what would happen to this particular quantity? Each of these quantities, that those would also tend to 0, correct? That's something to just keep in mind. So in fact, when we're letting delta x to tend to 0, each of these lambda i's is also tending to 0. So let's look at f of z, which is equal to f of x. So if lambda 1 through lambda n are the eigenvalues of this particular matrix, what are the eigenvalues of I plus this matrix? Correct. So it's 1 plus lambda 1, 1 plus lambda 2, up to 1 plus lambda n. These would be the eigenvalues of this particular matrix. Okay, that's something that we have. And what is the determinant of a matrix in terms of the eigenvalues? It is just the product of the eigenvalues. So this is this plus log product I equal to 1 to n, 1 plus lambda I. Okay, that's what we have. This is nothing but f of x plus, since it's a log of a product, this is just summation I equal to 1 to n. I equal to 1 to n of log of 1 plus lambda I. Okay, this is what I have. Now I need to be able to approximate this particular quantity. Okay, Taylor series expansion, what would this look like? What is log of 1 plus x? 1 plus plus x square by 2 and so on. Correct? So I can write this as f of x plus summation I equal to 1 to n of the Taylor series expansion of log of 1 plus x. So this is just lambda I plus some function which is smaller, much smaller than lambda I. It's at least lambda I square. So it's lambda I square by 2 plus lambda I cube by 3 and so on. Correct? So this is, I'll write this as some function that tends to 0 faster than lambda I. Okay, in fact it tends to 0 at least as fast as lambda I squared, whatever. So basically if I take this divided by lambda I, then this quantity would just tend to 0 faster than lambda I. Okay, so this is just f of x plus summation I equal to 1 to n lambda I plus summation I equal to 1 to n lambda I. So essentially this term tends to 0 faster than summation I equal to 1 to n lambda I. But what is this equal to? This is the sum of the eigenvalues, so it is just the trace of this particular matrix. Of which matrix? X to the minus half delta x, x to the minus half. So this is f of x plus the trace of x to the minus half delta x, x to the minus half plus little o of, again, the trace. So this is f of x. What is trace of a times b in terms of, if a and b are symmetric square matrices, then what is trace of a times b versus trace of b times a? Yeah, they're equal, right? So trace of a times b is simply equal to the trace of b times a. Again, we're assuming that all of these are symmetric matrices. So trace of x to the minus half delta x, x to the minus half is the same as trace of delta x, or trace of x to the minus half times x to the minus half times delta x. Which is f of x plus trace of x times delta x plus some quantity which decays much faster than the trace of x times delta x. Sorry? X power minus 1. That's it. So x inverse times this. Correct? But what is this equal to? We saw the trace is basically the inner product. So this is just the inner product plus the inner product between x inverse and delta x plus some term that decays much faster than delta x. So from this, what would you conclude as the derivative of f of z, f of x? It's x inverse, right? So the derivative of f evaluated at x is simply equal to x inverse. Yeah.
So on the previous slide,
Correct.
so we have written that log product of 1 plus lambda.
Correct.
How have we written?
So firstly, lambda I, lambda 1 through lambda n are the eigenvalues of this matrix. So what are the eigenvalues of I plus this particular matrix? 1 plus lambda 1, 1 plus lambda 2, and so on. But what is the determinant in terms of the eigenvalues? So the determinant is equal to the product of the eigenvalues, right? So the determinant of I plus this would simply be product of 1 plus lambda 1 times 1 plus lambda 2 up to 1 plus lambda n. Does that clarify your question?
Yes.
Any other questions? Okay, it was a rather laborious calculation. We used a bunch of different techniques to get to this. So take time later on to go through this in a little more detail. But the main point that I wanted to illustrate here is that at times it is not evident how to calculate the derivative of a particular function, in which case you will have to resort to first principles. Okay. If you have a function defined on Rn, then things are pretty much straightforward. You can just compute the partial derivatives, find the Jacobian, and you get the derivative. But in such complicated cases, you need to be able to find the derivative from scratch. Right? And this function log of determinant of x is something that arises very naturally in the context of wireless communications. When you want to find the maximum throughput over certain multiple antenna channels, the quantity to maximize turns out to be log of determinant of some particular matrix. And the maximization is performed over all covariance matrices that satisfy some particular constraint. Okay, so if we wanted to solve such an optimization problem using some technique like gradient descent or Newton's method, then we would need to find the derivative at every given point. And now we have a simple expression for the derivative itself. It's just x inverse. Okay, so that's something we can compute. All right, and just as a sanity check, what happens in one dimension? So in one dimension, what is determinant of x equal to? It is x itself. And what does positive definiteness correspond to? That x should be greater than 0, x should be positive. So log determinant of x essentially translates to log of x. And what is the derivative of log x? It's 1 by x, which is exactly what you get over here. Correct? So indeed, if we had to sort of guess what the derivative of f should have been, then that would be 1 by x, which is just x inverse. Right? So that that intuition extends in this particular case. Right? Any questions? Okay. So now that we have this, we know how to compute derivatives of sort of simple functions, right? But suppose we have more complicated functions, then either we have to find the derivatives from scratch or use some other tools. So in particular, suppose you can write a function as a composition of simple functions. Then you can find the derivative more easily. So suppose I have some function h of x which can be written as some g of f of x. Okay, so again this can be very general. I can have let's say f from Rn to Rm, g from Rm to Rk. Okay, so h would be a function from Rn to Rk. What would be the derivative of f? What would be the dimensions of the derivative of f? So the derivative of f would be an m by n matrix. The derivative of g would be a k by m matrix. Okay, and the derivative of h should be a k by n matrix. Now again, let's go back to the chain rule for derivatives that you have seen. What is the chain rule for derivatives? Suppose I can write, suppose all of these are univariate functions and h of x equal to g of f of x, then what is the derivative of h? So it is just g dash of f of x times f dash of x, correct? And that is what happens in this case as well. So suppose you had to guess what the derivative of h of x is. Again, remember this is a k by n matrix. What would be your guess? Yeah, so it's d, the derivative of g evaluated at f of x, right, times the derivative of f of the derivative of f evaluated at x. Okay. Again, the notation is not really the best that I'm using over here. In fact, I should be writing this dh of x as dh evaluated at x, but this again, you should remember that this is a matrix, and this is dg evaluated at f of x, and this is df evaluated at x. Okay, so let's look at an example. Suppose I have f of x equal to the 2 norm of ax plus b square. My goal is to find the derivative of f evaluated at x. Now again, I could potentially just write this expand this particular quantity out and evaluate the derivative. But an easier way is to write this as a composition of two functions. So this is g of f of x, where g is simply the 2 norm square and f is simply ax plus b. So what is df of x? Times df of x. So what is the derivative of 2 norm of some y square? 2 times the corresponding vector transpose. So that would just be 2 times, what is f of x? It's ax plus b, so this is 2 times ax plus b transpose times the derivative of f evaluated at x. What is the derivative of f evaluated at x? That is just a. Correct? Again, is it just a? It's a transpose. Okay, so the derivative of f is simply 2 times ax plus b transpose times a transpose. So what is the gradient of f of x? Correct. So it's just the transpose of this particular quantity, which is just 2a times ax plus b. Okay, so similarly, if you are given more complicated functions, you can just use, the easiest way to go about it is to try to use these chain rules. All right, any questions? All right. So just as we've defined the derivative, we can also define the second derivative, which is just the derivative of the derivative. All right. So d square f of x, this is simply the derivative of the derivative of f. So if f is a function from, let's say, Rn to R, what are the dimensions of f of x, of df of x? So this is in R 1 cross n. So it's a 1 cross n vector with real entries. Right? So the derivative is in fact a function. Correct? So the derivative is a function. So it's a function from Rn to R. You can think of it as a function from Rn to Rn. Correct? So what would the second derivative look like? So it's a function from Rn to, so again, if you have a function from Rn to Rm, the derivative is an m by n matrix, right? Just keep that in, always keep that in mind. So since we have a function from Rn to Rn, the second derivative should be essentially a matrix, correct? An n by n matrix. So this is just R n by n. And suppose I look at the derivative. What is the derivative of f evaluated at x equal to? It is dou f by dou x1, dou f by dou x2 up to dou f by dou xn. Okay, so this is the function. So it maps a vector x to this particular vector. So what would be d square f of x? So that should be an n by n matrix with the partial derivative of each of these quantities with respect to each of those variables. Okay, so that would just be an n by n matrix dou x1 square f by dou x2 dou x1 okay, and the transpose of this matrix is called the Hessian. So effectively, when we had the second derivative of wherever we had the second derivative of a univariate function, the natural extension is just the Hessian matrix. Right? So in the rest of this course, we'll mostly look at functions over Rn, univariate, so functions from Rn to R, or sometimes we'll also look at functions from classes of matrices to R, just like the example that we saw previously. Okay. All right. So, any questions? Which one? It is. They're both the same. Correct. So, the transpose of this matrix is equal to this matrix itself. Assuming that, of course, all of these partial derivatives exist. That's a fundamental assumption that we're making. But whether I talk about the second derivative or the Hessian, they're essentially the same. So we'll typically use del square f So let's consider the matrix. Let's consider the following function f of x equals x transpose ax plus b. What would be the Hessian of this particular matrix? Yep. So what is the derivative of this? So df x is just A plus A transpose times X. What is the derivative of this particular quantity? Just A plus A transpose, the whole transpose, which is just A plus A transpose, because this is anyway symmetric. So d square f of x is simply equal to A plus A transpose. Alright, so, and just as we had chain rules for derivatives, we can again use this, since it holds for any derivative, it also holds for derivatives of derivatives. So you can also use the chain rule to evaluate the hessian. Okay. Any questions? Okay, so I think this is a good time to have a short quiz. Do you all have your cell phones? Does anyone not have their cell phone? Yeah, you don't have a cell phone? I can just take a sheet. Sorry? You can just write it in the sheet and write the answer. So you can all maybe spread out, just two people in one desk. It's going to be very short. Okay, so we'll do a quick review of linear algebra. Again, our time is limited, so we just go over the definitions. The lecture notes that are posted on the website contain a lot more detail, but you should also go through your matrix theory or linear algebra notes in more detail. We won't prove most of the things, but maybe here and there towards the end we'll try to prove some concepts. Okay, so very quickly, let's try to define what a vector space is. So what is a vector space? Again, we'll assume that all vector spaces are over the reals. Okay. So what properties does a vector space have to satisfy? Okay, so formally what is a vector space? Okay, so what are the operations on vector spaces? So let's call it V. There's some operator called addition, which takes two vectors and outputs another vector, and another another operation called scalar multiplication, which takes a real number, a vector, and outputs another vector. Okay, so what property should the vector space satisfy? Commutativity. So addition should be commutative. Let's just go over all the properties that addition should satisfy and then go to scalar multiplication. Okay, even before that, associativity. So essentially it says that the order in which you add vectors doesn't matter. Okay, what else? So there should be an additive inverse. So there is a zero vector such that 0 plus x equal to x for all vectors. Sorry? That's the identity, yes. Correct. So first you need the identity, so then we can go to the inverse. So then for every x you need an inverse, an additive inverse. X. There's another vector which we call minus x such that x plus minus x is equal to the zero vector. Right? What else? Let's go to multiplication. What property should multiplication satisfy? What is commutative in multiplication? So it's always, it takes one scalar and multiplies with another vector. Right? Associativity, right? So it has to satisfy associativity. So alpha times beta times x is the same as alpha beta times x. Beta in R and x in the vector space. Because you need some form of distributivity. Correct? Yes. So alpha times v1 plus v2 is the same as alpha v1 plus alpha v2, and similarly alpha plus beta times v1 equal to alpha v1 plus beta v1. Anything else? Correct. So there is a multiplicative, the multiplicative identity, which is the one in the over the reals. It does not change the vector itself. So 1 times v equal to v. Okay, so we have these definitions. So let's look at some examples of vector spaces. What about Rn, Rk? R to the n is a vector space, right? What about the set of all n by k matrices? Right? This is also a vector space, that essentially isomorphic to Rnk. What about the set of all rationals? Or say k tuples of rationals? Does this form a vector space? Yeah. So k length vectors with each vector being a rational number. Is this a vector space over the reals? How many say yes, this is a vector space over the reals? How many say no, this is not a vector space over the reals? Okay, why is it not a vector space? Correct? Correct. So it's not closed. All right. So if I multiply a vector over here with an irrational number, then I don't get back a vector in this particular space. Doesn't matter. That's why I asked if it is a vector space over the set of reals, right? So it's not closed to begin with. So scalar multiplication is not a closed operation if we assume that this is the space V. So this is not a vector space. Okay, so let's look at slightly more complicated examples. What about the set of all positive semi-definite matrices? So I'll define S plus as set of all n by n symmetric PSD matrices So again, the first thing that you always have to verify to check whether something is a vector space is whether all the operations are closed. Okay, and only then you can check the remaining properties. Okay, so if I take two PSD matrices and add them up, do I always get a PSD matrix? Yes. So if I take, and why is that the case? Correct. So if I have A and B PSD, then X transpose AX and X transpose BX, they're both greater than or equal to 0 for all X. So if I take A plus B or any linear combination that's greater than or equal, so if I add them up, X transpose A plus B times X is greater than or equal to 0 for all X. But is it scaled but is it closed under scalar multiplication? What if I take minus A? Is it still positive semi-definite? Yes. Yeah. The eigenvalues. No. What if I take minus A? So if lambda 1 through lambda n are the eigenvalues of A, then what would be the eigenvalues of minus A? Minus lambda 1 up to minus lambda n. So are all the eigenvalues non-negative? They're all non-positive, right? So this in fact is not a vector space over R, right? But suppose that we sort of relax this and only wanted non-negative linear to be closed under non-negative linear combinations, then it would satisfy, then it's closed under non-negative linear combinations. And we'll see a special set that satisfies this. In fact, we'll see that it's called a cone, and this set of symmetric PSD matrices forms a cone. But what about the set of all symmetric matrices? Is that a vector space? Is it a vector space? So firstly, it's a subset of all matrices. This in fact turns out to be a vector space. Right? And what is the dimension of this vector space? A general n by n. Yeah. It's a subset. It's a set of matrices, right? So how many basis vectors do you need to generate the set of all n by n symmetric matrices? N basis vectors? Are you sure that's enough? Okay, what about Rn by k? What is the dimension of the set of all n by k matrices? How many basis vectors do you need? N? Yeah? Is that enough? Again, this set is the set of all n by k matrices, correct? Set of all possible n by k matrices. And you need to be able to generate every matrix using a linear combination of some subset of basis vectors. So how many basis vectors would you need? Okay, so maybe we'll stop here, think about it, think about both this case as well as this particular case. Okay, and we'll reconvene in the next class.